Okie dokie, 2015, level 2 mechanics. Let's do this. So we've got Janet who arrives home and she's parked the car on a slope that's 12 degrees to the horizontal. Draw labelled arrows to show the individual forces acting on the car. Easy peasy. So to stop the car from rolling down, we've got friction, which is acting up the slope, okay? So friction, let me do that in red. Friction, which is stopping the car from rolling down. I'm going to label it like the question has asked me. If. Then I've got my lift force, which is perpendicular. You have to draw it perpendicular to the surface. And I'll label it FL, lift force. Then I've got my gravity force, which is acting straight down. Okay, it has to be straight down. And I'll label that FG. Cool. So that question is done. Moving on. Explain in terms of forces acting on the car, how the car remains stationary on the slope. You may draw a vector diagram to help your explanation. So we have to explain why the car is stationary on the slope. And let's start off by drawing a vector diagram. Okay, so to draw a vector diagram, you have to add the vectors head to tail. I'll start off with gravity, which is acting straight down, FG. And then I'm going to pick my lift force, and I'm going to keep the angle exactly the same. Okay, it's on that angle as shown on the diagram. I'll label that as well. And then I've got one more vector left, and that is going to be added to the head of my previous vector. So you can see that all the tails are attached to a previous head of a vector, and that's how you do it. And I'll label that F. Cool. All right, so to save us trouble later on, what I might do is also add in this angle over here into my diagram, the 12-degree angle. But I can't just pop it anywhere in the triangle, so let's figure out where this angle goes in this triangle. And I've got a little nifty trick for that. So first I'm going to simplify the diagram. So this is my car. This is the friction force, FF, and it's along this flat surface at 12 degrees. Then I've got my lift force, which is perpendicular to that slope, FL. And then I've got my force of gravity, which is going straight down. So my trick to work out where this 12-degree angle goes, because currently it's in between this friction force and a flat surface, and that flat surface is not a vector, so we don't even have that flat surface as a vector on our diagram. So to figure out where this 12-degree angle goes, I'm simply going to displace my force of gravity and pop it in between my two vectors FL and FF. Let me just move FL, the label for FL, over here. Okay, so now that I've got my FG displaced and it's in between my two vectors, I'm going to do a little bit of highlighting to show you what's happening. So in between FG and my flat surface is a 90-degree angle, okay? So a part of this 90-degree angle is made up by the slope. How much of it makes up this 90-degree angle? How much of the slope makes up the 90-degree angle? Yep, 12 degrees. So out of the 90 degrees, 12 degrees of it is made up by the slope. So what is the remaining angle going to be? All you have to do is 90 degrees minus 12 degrees to figure out that this angle over here is 78 degrees. Okay, because 78 plus 12 degrees equals 90 degrees. So cool. Let's keep going. We've got another 90-degree angle occurring between FL, our lift force, and FF, our friction force. Can you see how that's 90 degrees? We've worked out previously that the angle between FG and FF is 78. Okay, so out of this 90-degree angle, 78 degrees of it is made up between FG and FF. Okay, so what is this remaining angle going to be? All you have to do is 90 degrees, go 90 degrees, take away 78 degrees, and you're left with 12 degrees. This is great. We can use this information and plug it into our triangle. So we know that between FL and FG, we have the 12-degree angle. What I will add is the 90-degree angle in my triangle. So where does it go? Well, according to my diagram, there's a 90-degree angle occurring between FL and FF. Okay, FL and FF. Okay, so on my diagram over here, I can do a little 90-degree angle in between FF and FL. Right, you're going to see how that's going to save us trouble later on, but let's continue answering the rest of B. So we have to explain why this car is stationary. Well, we can say according to our vector diagram, this shows that Fg, gravity, Fl, lift force, and Ff, friction force, or terrible force, are balanced with one another. Therefore, the forces are in equilibrium. Okay, so because of this, the car is stationary on the slope. Okay, this is why the car, terrible, sorry team, the car is stationary on the slope. All right, that's basically our answer. So if we can draw a vector diagram for something, this shows us that the forces are balanced with one another, okay? So because the forces are balanced, there's no net force acting in one certain direction, okay? And because of that, the car is not going anywhere. There's forces still acting, but they're balancing each other out, allowing for equilibrium, allowing for the car to remain stationary, okay? So that answers part B. Final part, we've got part C, and it's asking us, or it's telling us, the mass of the car is 1,500 kgs. That might be important. Carry out calculations to show how forces keep the car stationary while parked on the slope. You may draw a vector diagram to help your calculation. So I've already done a vector diagram, but we have to calculate and show that these forces are balancing each other out with numbers. So what do we do with a triangle? We have to use trigonometry. Okay, so I might just copy and paste this triangle down here so we can use it for this question. Copy, paste. Okay. So for trigonometry, I need to make sure that I have an angle and a known side, Currently, I have 2 angles and no known sides. However, the question gives me some information. It's telling me that the car is 1500 kgs, and this is a mass value. What can I do with a mass value? Well, with a mass value, I can work out the force of gravity. Okay, I can work out this force of gravity, and then I'll have a known side. So let's go ahead and do that by using, I'm just going to write force of gravity, just to be clear with what I'm working out. I can use this equation, F equals ma, where F is the force of gravity. Okay, so the mass is 1500 kgs times acceleration, which is 9.8, okay? And then plugging that into my calculator, I get 14700 newtons. So that is the weight force of gravity of the car, okay? So we know that Fg is equal to 14700 newtons. Cool. So now we have a side and we've got an angle of 12 degrees, and now we can work out one of these other forces. We're going to eventually work out both of them. So I'm just going to start off by working out the friction force first. Before going ahead, label this triangle up. We've got our adjacent over here because it's in between these 2 angles. We've got our opposite because it's opposite the angle of concern, which is 12 degrees. And we've got our hypotenuse, which is our longest side. So to work out friction force, I'm going to use my hypotenuse because it's the known side, and my opposite because that's the side I want to find out. So let's go ahead and work that out. So if I'm using H and O, or O and H, that means I use the SOH function, which is the sine in trigonometry. So sine theta equals O over H. Substituting values in, I've got sine 12 equals O, which is what I'm trying to figure out, and H, which is 14700 newtons. I want to find out what O is, so I have to get rid of what's down here. So I times it by itself. I times the other side by the same thing. And then that leaves me with O equals 14700 times sine 12. Plugging that into my calculator, what did I get? I got 3056.302 newtons. Okay, so now I know that my friction force is 3056.30. Let me move this across. It's this value right over here. Okay, so let me highlight everything. I've got my force of gravity and my force of friction. And then now I'm going to finally work out my lift force. Okay, my lift force. Scroll down a little bit. To work out my lift force, I'm going to use my force of gravity, which is the hypotenuse, and adjacent, which is my lift force over here. Okay, so if I'm using A and H, that is K, which is my cosine function, and so cosine theta equals A over H. Okay, substitute things in. H is 14700 newtons. I want to figure out what A is, so I have to get rid of this divide by 14700 by timesing it by itself. Cancels it out. That means I have to times this side by the same thing, and I'm left with A equals 14700 times cosine 12. Plugging that into my calculator, I got 14378.77 newtons. Okie dokie. So I know that this side here is equal to 14378.77 newtons. And I'll highlight that. So I've worked out all the forces, okay? I've rewritten the forces of our calculated values up here. And we just basically have to understand how these forces are balancing one another out. And you might be tempted to think, oh, these values are not the same, so how are they balancing each other out? Well, I have a little analogy for you. So I want you to think of tug of war, okay? Our favorite sport or game to play during house events. And so we've got 3 teams. It's a 3-way tug of war thing happening over here. So we've got team FL, team lift, team friction, and team gravity. So each of these teams have to ensure that they're pulling the right amount of force to stop the other team from fully pulling this rope onto their side. So if we think of team gravity, okay, and team friction over here, team friction is pulling the rope by this many newtons, okay? Team friction is pulling the rope by this many newtons. So the team gravity has to pull their end of the rope by an equal amount of newtons to stop or counteract team friction, okay? Team friction's efforts. So they've got all these newtons, okay? All these newtons of force to be able to pull this rope, but they're only applying this much of force, okay? This much of force to make sure that they're counteracting the friction force just enough. Not too much or too less, but just enough. Similarly, if we look at team lift over here, to stop team lift from pulling the rope all the way to their side, okay, team friction and team gravity kind of work together to counteract team lift's force, okay? So they work together and use a portion of their total force, which adds up to the team lift's force and counteracts it, okay? I know it's pretty tricky to maybe wrap your head around what I've just said, but feel free to email me if you need further clarification. But we do need to put this into words, okay? So just to remind ourselves, we need to carry out calculations to show the forces, how the forces keep the car stationary, okay? So this is how I'm going to say it. The forces, the forces balance each other out. How? As a component of the gravity force will balance out the friction force, and a component of the gravity force and friction force will balance out. I've had a brain blank. Balance out the lift force. Okay, so with reference to these numbers, okay, this is my written answer that goes with it. And that's it. So this question in total, collectively, was worth an excellence. Feel free to have a look at the marking schedule 2015. No Brain Too Small has access to the marking schedule for this question. Go check out how it's broken down. But that's all from me. Hope that made sense.